Hello everyone and welcome to our next panel of today's One API Dev Summit. This one is Accelerating Software on the Edge. Let me give a quick intro to the panelists before I hand over to them to get started. A couple of them you'll already recognize from earlier on today. So this panel features Manoj, who is Director of AI Product Management at Qualcomm. And he's been one of my co-hosts throughout the day, so he'll be very familiar to you. He is being joined by Andrew Richards, who's the founder and CEO of CodePlay and participated in our earlier panel on open source software. Also joining them is Alex Pym, one of my colleagues at Imagination Technologies, where he is our Vice President of Compute and is currently helping to shape our company's future direction as a member of the Technology Office. And leading them today is Zain, a senior tech lead at the Autoware Foundation. Zain is instrumental in preparing Autoware for the prime time and ready to be used by OEMs and tier ones in their autonomous vehicle development journey. Right. I understand that the panelists today are very keen to take questions from the audience. So if you do have something you want to ask of any of them or all of them, feel free to type it into the Q&A widget at the bottom of your screen, and they will get to it towards the end of their presentations. And with that, I will hand over to our panelists today. Thank you.
Hello, everybody. Thank you very much for the very nice introduction, Eleanor. Really appreciate it. And very glad to be here with Alex, Manoj, and Andrew to have a really interesting chat. So with that, I thought we'll just kick off the discussion with yourself, Manoj, and dive right into the content. So I wanted to begin by asking you some really kind of high-level questions. So maybe you could just introduce what is One API, and why is it beneficial for developers to consider using One API for having broad customer adoption of their applications?
Yeah, thanks, Jan. So, from my perspective, right, One API is mostly for used for simplicity, right, for developers targeting multiple hardware. As we see, there's growth of their own accelerators or CPUs, GPUs getting increasing. The work which developers needs to do now has increased on the multifolds. And what One API provides us is unification. That's important, and as I call simplicity, targeting multiple architecture. Also, from like what I think as part of, I've been part of One API in my previous job also is it's like you have a Swiss Army knife kind of stuff. You have multiple place, you can try multiple tools are there, right? And you don't want to go and learn everything, and targeting multiple platform. One API is a place where you can start with, right? And you can, it's a versatile tool. You works, it can at the interface level, developer can interface with single development tool, and backend can be IHV based.
So it really simplifies the journey for a developer to go
Yeah,
from their application to go to the end hardware, whatever that end hardware might be. It's
and
just one input and then multiple outputs. Great. So at Qualcomm in our previous chats, you mentioned a lot of interesting use cases that Qualcomm is developing. So what are some of the end use cases which really excite you the most regarding adoption for One API?
yes, man. Again, early days at Qualcomm on One API UXL, but what we see is a trend is you have use cases are now not targeted only for one hardware centric, right? And that hardware is not like I'm talking is one accelerator on the cloud and multiple all the accelerators on the cloud. It's mostly between moving from one type of device, let's take mobile, right, to auto, to AI PC, where now Qualcomm is also vested in that, and then of course the cloud and IoT, right? As that devices grow, we are looking at very high level abstraction layer, and Qualcomm will continue, and all IHV will continue investing in there to make their libraries based on their own hardware. And this is where we see use cases coming from some vendors which will run across these devices. We are not talking about even just across one type of accelerators, like cloud can have 5 different vendors. These are different devices, and that's where we are looking at long-term heterogeneous computing, right, where you can have the same app running on multiple places, same experience. And from a developer perspective, back to simplicity, what One API provides us, you will write at the higher level. Of course, there will be all all IHVs are doing their own magic, but we will be able to bring same experience across device of compute, right? So
Yeah. So it could be the same thing running on edge. It could be running in cloud. It could be running on PC. That's really
and
it
autos,
could open up
yes,
any,
yeah,
yeah.
yeah,
And obviously on a car, that's something which
yeah,
I'm really excited about, of course.
yes.
So that's definitely a very big, I think, advantage of this framework and something that's very attractive about it for sure. So you mentioned these different frameworks and these different use cases and applications. So from a developer perspective and a technology perspective, how easy is it to kind of port a technology that maybe isn't built for one device or one application to a different device if it's been built with one API in mind?
I would take both places. Something which is what we have seen, something new. Let's start with something new, right? You are
Mm.
creating a new architecture and all, and if you keep one API in mind, it will be easy to deploy because the architecture, how it is, abstraction is created is the backend can be all different, but you can create your own architecture, which a new
Mm.
architecture which is already deploying for multiple devices in mind. Okay, that's the easy part, right? But there are many applications we have seen in now it's years is they're already supporting some kind of GPUs, right,
Yeah.
or some kind of accelerators. There we have, from the experience what we have looked at, the abstraction what we are trying to provide through UXL, through one MKL or at a high level or Syscall APIs itself, it can be more generic as much. So once you start, if you have written for one vendor as of today and you're not based
Mm.
on one API spec, there will be some work needed, but that is minimal. Okay. We will have some case studies. I think blogs have been published, but the time it takes from already deployed architecture on one GPU hardware company going to one API spec, there will be like a easy way of I would give is you can have some conversions we do provide where you will be able to get from one vendor to another vendor. And once you are on one
Mm.
API architecture, then it's back to simplicity.
Yeah, yeah, that makes a lot of sense. And in our kind of conversations regarding Autoware, it's a very large software stack, and we've already talked about the kind of dual approaches of do you think about adding one API on a new project from scratch versus using it and doing the integration from existing software frameworks that have been developed. And I think you were a big proponent of both approaches being really valid
Yes.
and really simple and easy for developers. So I think that it's definitely something that, at Autoware, we're looking at very closely, and we have the working relationship with UXL. So it's something that people will be able to see in the open source domain and to see it in action in this very exciting use case of autonomous driving. So thanks for the kind of interesting chat there, Manoj. I wanted to take the conversation to you, Andrew. So you're kind of a key part of the whole vision and thinking behind this entire development. So I thought I'd kind of open with just asking you for your vision at the North Star level behind one API, behind one Excel. What is the kind of ultimate North Star goal that you're trying to achieve?
Certainly, it's our goal is to be the open source, open standard way to develop software for accelerated computing. So many years ago, I've said this before, my background was in video game development, and I thought, oh, these GPUs could be used for other stuff. But nowadays, there's just so much use of specialist accelerators, DSPs, and you got them across the chip, giving you all of this performance to do amazing things. And so if developers can just develop on one system, like they can develop on their normal PC or their laptop and use the CPU and the GPU in that situation. And then, for edge devices, what you find is people want to do quite specific processors on the chip to give better performance per watt for that software. Then just being able to take that software and say to developers, right, you can develop it on a PC today, and then in 2 years' time, there'll be this new chip that's going to run it at like a tenth of the power consumption and still have the same performance. I think that's a very powerful thing. And so, if we're talking about a self-driving car, for example, people do all these research where they stick basically a supercomputer in the back of the car, right? But being able to lower that power consumption by looking at the software written on the supercomputer in the back of the car, and then being able to get it in the car and cheap enough to run the car, that I think is a fantastic thing. And that creates a whole lot of problems that we've been working on to solve. But the key thing of actually being able to develop that software on a supercomputer in the back of the car, that you can do today, and then we just need to make it easier to solve getting it into the car. And that involves things like, how do you bring it to more efficient processors, and how do you solve the problem of functional safety, and how do you have a roadmap of actually the compatibility that allows you to get the performance that you need on those low power systems.
Yeah, totally true. I've seen many car trunks. You open the boot of the car, and it has literally a cluster with about 4 different GPUs, and each of them are very high end. They're each drawing 300-400 watts, so you've got 1.2 kilowatts just for the compute, and that's not even thinking about anything else that you might have in terms of drive-by-wire systems. And then you have the auto OEMs who are kind of at the other end of the spectrum, and they're talking about, oh, this shouldn't have more than 100 watts or 50 watts, and it should be less than X number of dollars. So with the developer experience, especially in the autonomous driving space, it's just throw everything in there. And then suddenly when you get to the customer, it's like take everything away. So that is a very big jump. And anything that makes that big jump easier or can make it into little steps is a really useful, very useful thing. And I mean, in my personal experience, I've worked on the cluster computers in the back of the car, but I've also had a gaming laptop running certain perception algorithms. And again, going from something like that and be able to port that to a little kind of processor that is on a small form factor, low power kind of form factor would be really useful, because you go from prototype to product really quickly. So that's a really bold vision statement, and I'm excited to see kind of that vision statement be realized. So,
but now you say it. Sorry, I just wanted to. Now you say it. We've got 2 companies on this call who took what was like impossibly high-end video game graphics, right, and then brought it down onto a mobile phone. And when I first saw them starting doing that, I thought, how is that ever going to work? And yet you do get incredible graphics on these incredibly low-power devices where the battery lasts all day. So it is possible. We can do it. We've got to get the software working. And of course, what we've got to do is we've got to get Autoware running on UXL Foundation software stack, and then we can shrink it down.
Yeah. I mean, we've had a lot of discussions. Alex has been doing really great work on actually beginning that integration, and we'll have a chance to talk about that in more detail. And specifically, the kind of work that I'm leading in Autoware is very much customer focused. So it's more of a highway autonomy system for passenger cars. And it's quite different from what we have in Autoware at the moment, because this stack is very vision heavy, very neural network heavy, will even have some end-to-end autonomous driving components. And so having that acceleration there and being able to get it into that form factor for an end automotive customer is going to be super important. I think that's going to be a very powerful demonstrator of UXL. Also for the robotaxi version of Autoware, but also this kind of passenger vehicle version of Autoware.
And so can I ask you a question that often comes up in this, right? Is all of that just one big neural network, or have you got lots of smaller neural networks, or have you got lots of neural networks and a load of other algorithms, all of which need to be accelerated?
It's a hybrid approach. So it is not the one big neural network to drive the car. That's what you would call end-to-end autonomous driving. And that is an approach being taken by different companies, particularly Wave in the UK. You've got Waabi, it's a trucking company in the US. Tesla, is very famously announced that they've used end-to-end autonomous driving in some of their latest software updates. But we're taking more of a kind of component-wise approach. So there are specialized neural networks for perception, and they work on different sensing domains. So for example, a neural network for the vision pipeline, a neural network for the radar pipeline, and then a neural network that does the kind of bird's eye view and fuses that data. And separately from that, there is a deterministic kind of computer vision based part of the software that is there to ensure the core safety of the system. And so that will, be written first probably in just C++. And then the goal will be to be able to parallelize that as well. So it is more of an ensemble stack with different components and different streams, because it's very important to have redundancy in the system. And also the other reason why we chose this approach was explainability. So you can inspect the kind of output along the pipeline and to know how did the car go from input to this world model of where the objects are, where the lanes are, to the end decision. Whereas with one big neural network, you just crank the handle and out comes the driving path. And the other kind of challenge with that approach is that, especially for highway driving, people are driving about 280 billion miles on highways and passenger cars every year. And so you need to have a very, very high performance. So 99% isn't good enough. 99.9% isn't good enough. You need something like 5 sigma performance. And to the best of my knowledge, there's not a single neural network in the world that has achieved that level of performance. And we can also talk more about LLMs and vision transformers and things like that. And going towards AGI, maybe we can just give enough data and then the car will just learn to drive. But I think for now, at least from the safety and product perspective, it makes sense to just kind of have the component-wise approach. But there are some end-to-end things that we're going to have in there that I think are pretty exciting.
And you highlight why we have lots of different components in one API, right? So we've got the C++ bicycle and stuff, but we've also got all of those different things to be able to handle the neural networks. I think it highlights the relevance of what we're doing. And I hope we're able to get it all working with you.
Yeah, I think.
I'm definitely excited about it. Go ahead, Manoj.
Yeah, so one more thing on that same question, right? On the creator space, what we have seen is, and maybe that's the same for auto side. Many times developers create base model, and because it's still they have not reached the accuracy, they prefer to start from the output of the previous one, right? And then they continue refining. So it becomes a sequence of like 5 models, 6 models, even though it's doing the same task, but it's at the end, they continue improving instead of starting from the scratch and say, oh, we create a very big model, which will be perfect. So they try to split those models. And at the end, let's take, if you get 50% accuracy, next model will be the output of that 50, and then you start again. So that's one of other trend we see is splitting of a lot of work, small neural models, and then they try to deploy instead of go back and start from scratch.
Yeah, it's very hard to train one big model. And I mean, you've seen examples of this, models with billions of parameters, tens of billions of parameters. We haven't really seen such huge models in cars yet. I know Tesla's FSD is up at around 1 billion parameters in their neural network. I don't think we're going to target that for this version of Autoware. But yeah, definitely it is harder to train one huge model than it is to train the little component models and to verify that you got the performance in that component level. We've kind of talked a lot, Andrew, and I guess I wanted to just, again talk to you about the safety aspects and standards aspect, because you've kind of spoken about, you mentioned it briefly, about being open in the development. Now, especially from an automotive perspective, as well as any other critical use case or high performance use case, having a safe system and being able to have the development live in the context of safety standards is really important. So what is the kind of one API UXL vision for not only building the frameworks, but linking up with the standards development?
Yeah, so this is a really good question, and you highlighted the key things. You talked about safe system. Whether a model is safe is about the accuracy that you talk about, but you also described a safe system. And one of the things that you did was talked about redundancy, like you've got a machine learning based system, but also an explainable system as well. So that's very much part of safety, is being able to explain things, but also be able to have redundancy and have 2 systems and be able to compare them. And you need to think about that at the system level, because actually these accelerators they're quite new. GPUs were designed for video games. So starting to look at safety, they haven't been studied in the same way at all in terms of how you handle errors and timing issues. And also there's all sorts of stuff, like you may get the right answer, but too late is a problem for safety. Or there may be a hardware error. And then how do you deal with that hardware error? Those are all really, really difficult problems. And so we've been working, we've got the SICL safety critical group, which is actually working on defining a standard for that. And we've got a safety group within the UXL Foundation as well. And what I found is companies that want safety are really interested in standards, because if everything's documented, you can study the standard, but you can also have redundancy, because you can have 2 standard components and then compare them against each other is another way of achieving safety. So I think actually the standards are a really, really good fit for safety. And what we now need to do is analyze all of this and go, what are the actual safety issues? And if you're new to safety, as some people in GPUs are, working with the safety people to go, right, okay, what does it mean to be safe? Sometimes it's quite surprising, but quite an very interesting field.
Yeah, I think it's especially for autonomous driving. A lot of companies have safety frameworks that they talk about simulation, they talk about sensing, they talk about the way their stack works. So they're only speaking from a developer and application perspective. But many times other aspects of safety are simply kind of mentioned, but there's not really a deep dive in it. For example, whether it's cybersecurity or, like you mentioned, safety of the system at the hardware level, at the kind of execution layer. Is it a deterministic system that if I crank the handle with the same input, I'll get the same output every single time, or will a bit flip or something else like that happen? So it's a really important aspect for, again, not just the development, but the path from development to the commercialization. Great. Thank you for those contributions, Andrew. So, Alex, I think I'll shift the conversation to yourself. So, you've been working with Autoware and getting into the weeds of actually integrating some One API libraries into the stack. So, I wanted to kind of just start with a high-level question of what do you see as some of the potential use cases for One API integration in the automotive and autonomous driving space?
Yeah, so we know that driver aids in the automotive industry are commonplace now, and they leverage machine vision, radar technology, lidar sensing technology, and there's various algorithms that are used to process that data and get those results. We have things like DFT, FFT for radar. We have point cloud pre-processing and processing for lidar. And then we have what we're familiar with, the deep neural networks for things like object and pose detection, object recognition, object tracking. The thing is, when those systems are implemented in kind of ADAS level 2 for just driver aid, not full autonomy, they're still quite high compute. So when you talk about a vehicle that can drive itself, ADAS level 4, you really are ramping up those compute requirements. And what we've seen and what we know from analysing these algorithms is that they are highly parallelizable. A lot of them are highly parallelizable and can run on architectures that are not CPU. They can run on GPUs. They can run on NPUs. How do we achieve that kind of shift from CPU to GPU? Well, the problem is with these algorithms, they're written for CPUs. Now, an algorithm written for a CPU can be ported to other CPUs with little effort. But moving them to a GPU or a different architecture like an NPU is much more difficult. So we see the code being written as portable code for CPUs, but it's not portable for GPUs or NPUs. And that's where One API comes in. We want to have libraries like One MKL and One DNN so that we can develop on one platform. That might be a platform of just CPUs. It might be a platform with other accelerators. But when we come to deploy those algorithms, they can be deployed on multiple different platforms: CPUs, GPUs, NPUs, other architectures. So you see that there's lots of kind of use cases in autonomous vehicles and autonomous software stacks for this. And we want to give not only the helping hands for developing those systems so that you're not tied to particular hardware, but you also want to be able to give the system designers more choice at the end for what they deploy on. As you say, not everyone wants a supercomputer in the boot of their car. They want to be able to put in the back of their car a computer that makes sense, an architecture and a platform that makes sense, that's very closely related to the energy requirements of the other parts of the vehicle, especially if it's an electric vehicle. There's power budgets that need to be adhered to. You want to be able to know that what's in there is exactly what's needed, nothing more, nothing less. Though obviously, if you're not putting a supercomputer in there, you get lower area benefits of manufacturing those chips, less power. And as I say, you get a system that is not a supercomputer and it works for those compute requirements for those algorithms. So yes, lots of potential use cases, lots of algorithms that can be parallelized, and we want to be able to parallelize them almost transparently, actually just being able to say, well, it doesn't matter where it's going, don't worry about where it's going to run. It can run on whatever the final target is or whatever any intermediate targets are.
Yeah, very true. I think your observation about how you discovered many algorithms running in the AD stack are parallelizable. I think because many times autonomous driving developers are spoiled for compute. They have often excess resources. And so the requirement to have those parallelizable algorithms is not always there, because you can have a very, very powerful CPU or a really powerful system, and so it will just brute force it. But as you mentioned, when you're going towards that customer journey, you don't want a supercomputer in the back of your car. You want something that makes sense, something that is affordable for the customer, especially if you're talking about a privately owned vehicle where you're buying the compute, the sensors, and the software. So yeah, I think that's a really key point to consider with adoption of this technology, especially in the automotive space. So in terms of the kind of libraries, we've had mention of OneMKL, we've had mention of OneDNN. Could you just give us an intro of what these are, what should they be used for, what's the difference between, let's say, using OneMKL versus OneDNN, what kind of workflows can be accelerated by one versus the other?
Yeah, absolutely. So OneMKL mass kernel library has been around for quite a while, and it predates the CNN revolution. It was for more kind of ground mathematics. It was to do things that were the algorithms that were more perhaps for industrial computing or for scientific computing, much more the kind of bedrock of science rather than the latest kind of new state of the art. So we have that library. That library contains a very clean and nice API for things like BLAS, so that's basic linear algebra subprograms, for FFT processing. It's also got level plaque in it. I think I'm not too familiar with that, but it has the capability of doing lots of matrix multiplication kind of functions. And the kind of thing that you would use in scientific and industrial use cases. The OneDNN is much more recent, and the reason we have the OneDNN is which I'm going to come to in a minute, is the way CNN deep neural networks work is they have lots of operations one after the other, and the way the data is fed to those operations can be in multiple different types of formats, and they're in what we call tensors, and those tensors can take on different shapes and different sizes. So whereas you could do a lot of what was in OneDNN with the original kind of OneMKL library, the OneDNN functions are tailored more for the kind of shapes and sizes of data that you get in convolutional neural networks that we've got today, as well as some other workloads. So what that leads us to is how do you choose the right library to use? You need to analyze the workload. You need, there's no point offloading an algorithm to a device that isn't catered for that, or isn't designed to do that kind of operation. And part of that analysis is of the memory usage and the movement of data in and out of memory, as well as the shape of the data. So to give you an example, we looked one of the Autoware modules, the NDT scan matcher, which is used for the localization in Autoware. It does millions of small matrix multiplications, not large ones, which we were kind of expecting without kind of diving further. And that doesn't actually work very well on a GPU, because you have to set up these algorithms, you have to get the kernels, you have to get the data in place, and you have to kick those off. And an overhead for millions and millions of small ones of those actually slows the system down. It doesn't speed it up. Whereas a CPU for small matrix multiplications can actually be configured to do a much better job. And actually, our GPUs specifically are tailored for large matrix multiplications and not small ones. So you need to analyze the workload properly to make sure what the decisions you're making make sense. I mean, if you again look at something like transformers, the attention mechanism in the prefall stage, that's a large, lots of large matrix multiplications straight up. So you use something like the gem functions in BLAS for that and get really good performance, because that's what the gem functions are there for. And you suddenly move that from a CPU that isn't so good at or isn't capable of doing those large matrix multiplications because they're compute bound. You can get better performance there. But then that sticking with transformers, if you look at one of the recent concepts, flash attention, that does something slightly different. That actually breaks up those large matrix multiplications and looks further down the pipeline and says, well, what operations am I going to do in series on this data, and can I pull all of that data at once, perform all those operations, and then push that back and ready for the decoder stage. So that you'd probably use something like OneDNN for, and I think there's talk of OneDNN, and certainly our own library supporting a flash attention kind of operation. But that needs to do several operations in a row, and the data format going into those operations will be specific. So you can see that, again, depending on the workload, it might make sense to do something like 1DNN, where inside those kernels, the operations are fused. They're performed all at once in place, so that you don't have to keep going back out to main memory and using up valuable system bandwidth in what is a very complicated system. Same goes for object detection. You've got large matrix multiplications and object detection. But when you're doing a convolutional neural network, you have operations adjacent to those matrix multiplications, again, that can be done at the same time and don't have to be kind of pushed out to memory, pulled back again. So again, 1DNN, that's why everyone who works in this will be familiar with a convolution operation in 1DNN. It does more than just the matrix multiplications. It does it takes in a specific format, which is a format shared by TensorFlow. And it does those operations in situ rather than kind of going out doing an operation and it does that by appending those operations to the back of the module to the kind of convolution operation. So you can get better performance, so you can lower bandwidth, and it just works. It works well. So yeah, you have to know what the workload is. You have to know what the data formats are going in, and then you can kind of make a decision as to what you want to use. If your data's in NHWC format, then you probably need to use 1DNN. If it's a matrix multiplication and you want to do it row major, column major, then BLAS will be fine for that. It's about what makes sense, and you should be able to come up with a good decision on what will work for that system.
Yeah, that's a very detailed answer. And I think that especially in Autoware stack, there are many things that are suitable for both workloads. And there are lots of interesting algorithms from a computer vision perspective that I think would be very beneficial for 1NKO. For example, optical flow involves a large matrix inversion, things like that. And stereo correspondence, which is a kind of a constrained version of the optical flow problem. A lot of times, that's just taken as a granted, but stereo vision, optical flow, motion tracking is very, very useful for an autonomous car. And there are neural network approaches that do that, but the classical computer vision systems still work pretty well, and being able to accelerate them is super useful. And especially in the kind of the passenger vehicle autonomy use case, as I mentioned earlier with Andrew, there will be quite a lot of neural network processing. So the vision pipeline, the radar pipeline, and then there'll be a step in the middle. So I would assume that's 1DNN acceleration because it's a neural network. But there's a point in the middle where you're doing a transformation, going from the kind of 2D view into the 3D view. And that, I think, would be something, again, super useful for 1MKO, because you would have to do a kind of a transformation on all of that data. Yeah, I think that once a developer knows the kind of structure of the code and what they can do, that they can make a recipe quite quickly and easily for how to go about accelerating
your job. Yeah, definitely.
So in our kind of previous chats, we've had this talk of where does one API sit in the kind of stack, and is it we have modules that use CUDA and so on and so forth. So it's not a replacement for CUDA. Is it a replacement for CUDA? Does it sit above it? Does it sit below it? Does it sit beside it? Where do you see kind of the level of integration versus using it versus replacing something you have?
Well, so in Autoware, yeah, there's several several algorithms there.
I mean, just to jump in, I would see one API as an alternative to CUDA. I think it's close enough that you can actually write software that shares code between CUDA and SYCL, if that makes sense. Like CUDA and SYCL are both C++ as languages, are C++, and they're close enough, and they're both really C++. So you can kind of hide the differences in if-defs. So you can actually write code that is compilable with both the CUDA compiler and a SYCL compiler, or you can write your code with SYCL and then use CUDA underneath. And then, because you can run SYCL and one API on an NVIDIA GPU. And then really the libraries that we've got are very similar to the CUDA libraries in a lot of cases, but they're standardized, and you can optimize them for a much wider range of hardware. So it is the bottom of the stack, right? It's not the top of the stack, but it is that bottom of the stack, but it's done in a way that does allow people to do optimizations for their hardware.
Yeah. There's modules in Autoware that have got offloading, and they use things like TensorRT. But there's also a lot of modules that are still on CPU using things like OpenMP and Eigen, and they are prime candidates for moving that to GPU. Collaboration with Autoware is allowing us to look at those modules, and find good places where we can do that. There's point cloud pre-processing, as I mentioned earlier. It's a great place to put one MKL in there. It's about opening it up to not just Power BI GPUs either. It's about making sure that anybody with a GPU or an architecture that can do these workloads well is able to use them without too much effort. We're bringing a clean and tidy interface to a system at a particular level. Once people get used to using that, they don't have to worry what the target will be underneath. As Andrew said, you can convert your some CUDA code and then you can run it back on an NVIDIA device through SYCL. So you're not even removing anything from that equation. You're just bringing abstraction a bit higher up, so that you have more choice as to what you run it on, and that's got to be good for developers, and it's got to be good for people designing the deployment target at the end of it all. So the other thing is by having that kind of clean API for one MKL, one DLN, also means that vendors like ourselves can put our own optimized low-level code in. We can write optimized kernels that work with our architecture, because not all GPUs are made the same. They have ways of doing things that can be leveraged, and we are able to hook in via the vendor kind of backend interface the perfect way of doing each particular operation that comes in through the top of that API. It's obviously great that we have generic OpenCL implementations at the back end of one API and those libraries, and they should work on every GPU. They should work on Power BI GPU. They should work on it. But you've not only got that, but you've obviously got the capability of using the optimized libraries as well to get every ounce of performance out of that target.
Yeah, absolutely. And I mean, the thing you mentioned about having the choice for the developer to deploy on different hardware, that's so important, because again, if the paradigm is not that just we're going to develop code for a demo, but we want to actually get it to a product, then especially in the automotive space, a lot of the higher levels of autonomy that OEMs are targeting, they're basically locking in with NVIDIA as the main vendor. But many of the kind of newer entrants into the automotive space don't necessarily want to be locked into a vendor or a software stack, and they want something that can be a bit different. And I think being able to offer the customer a broad choice of whatever hardware you have, whether it's using this processor or this accelerator, we can take our software, our application, and you can pick and choose. And even if the performance or the power output or whatever the specific characteristics are, like you mentioned, that are different for each vendor, at least the customer has the choice that, okay, we can work with vendor A, vendor B, and the software should just work across all of them. I think that's a very, very important requirement for the customer.
Yeah, because the development of these algorithms usually will start somewhere like the cloud or a data center, and what by doing that, without the concepts of one API and what we're trying to bring here, you're locked in. You're tied into the deployment being as the same kind of architecture as what you're developing on. That you don't want that. You want to be able to develop in the cloud using all the compute resources. You want to be accelerate everything you're doing for development. You don't want to have to use what you used in the cloud and the data center in the final product. You're decoupling the deployment from the development, and that is the essence of what we're trying to do. You're bringing that choice, and you're decoupling that initial development platform from where it's going to run in the final product.
And that's a huge challenge. The thing you just mentioned, in my kind of past experience of working in the field, I can tell you from a developer perspective that the kind of developer environment and the hardware and the resources you have versus what you have in the car, there's a huge gap in that. And then the gap of what you have in your prototype vehicle compared to what you want in your production vehicle, there's an even bigger gap in that. And the kind of barriers start to go up the minute you realize that, oh, I can't run this here. And the thing that runs here can't run over there. And so how do I go down this journey of, all of the resources in the world, to fewer resources, to very little resources? and very specific optimized code. So I think it's the perfect use case for these kinds of high performance applications.
Yeah, I agree.
And
Yeah.
maybe could you please talk a little bit more about the kind of the specific algorithms that you're currently working on to accelerate them using one API? Because you mentioned the entity scan matcher, but there's also a one DNN acceleration that I think is happening.
Sorry, so again, I didn't catch up so we looked at NDT and it wasn't quite right for GPU. We've identified so point cloud processing is quite a popular one because you've got the LiDAR sending all of this data at quite a high resolution, generating so many points, and you don't need all of those points from the LiDAR, not necessarily. You don't need all of that data. And one of the things we've identified is cutting, down sampling that data, making sure that all the important information is kept in that structure, but the stuff that's not so important and doesn't actually bring anything to it is dropped. And you do that before you even do anything with the data. Once you've downsampled that cloud, you send it to a neural network, and the neural network uses the output from that kind of pre-processing, the number of pillars and the features that it's organized in the structure, and you start to see how it can detect objects, how it can give you the bird's eye view, how it can detect the range of the things. There's so many stages in which the sensory data comes into the car and needs to be processed. So that's one we're focusing on right now, and there'll no doubt be plenty of others. And actually, the point cloud stuff is used in multiple places. It's used for the localization, and it's used for object detection and sensing. So if you can accelerate, at that point of origin, you're already increasing the rate of data going into two other parts of the Autoware system with one set of optimizations, if you like. So if you can optimize up here and it filters down to many other systems, then that you're on the win there. We're working our way through and just checking what the kind of algorithms are and whether they're suitable for offloading. It's a long process because Autoware is a fantastically complex software project, it's very comprehensive in the way and it provides options as well. It's not there isn't just one way of doing things in Autoware either. It's a place for prototyping. It's a place for trying out to see whether something works better or something works better with another module. So you've not only got several stages, but there's multiple options in those stages, which some are enabled, some aren't. There's a lot of algorithms to analyze in there for us, and work out which ones of them make sense to bring to an API backend.
Sorry, go ahead.
I was going to say, because we've got full programmability in one API, anyone can do that research and work out how to optimize some of these algorithms for highly parallel processors. So you have total flexibility, but we also have done some of the work for you.
Yeah, for sure. And I mean, the thing you mentioned, Alex, about exploiting the sparsity of point clouds, there have been huge bodies of work done on just that one thing of how do you develop a algorithm that doesn't have to necessarily look at every single voxel in the 3D space, because the smaller your voxel is, the higher your resolution, but then you have a lot more things to consider. So the point cloud preprocessor will be a big boost. I think we're already looking at point pillars-based 3D obstacle perception as one of the target candidates for acceleration. And certainly with the kind of work I'll be leading, there will be a lot of stuff that I'm excited to be able to work with you guys to do the acceleration, because it's a lot of neural networks in there.
Yeah, exactly.
Yeah, and I think that in terms of the actual logistics of it, we'll be quite soon be able to actually open the GitHub discussions for bringing this to Autoware, for sharing it with the Autoware members. And, I'll be establishing a work group quite soon related to the specific passenger vehicle automation. So we'll be able to begin the kind of formal process of integrating one API with the Autoware software stack and bringing it into public view, starting to get those first code commits up there on the GitHub. I think that's going to be really exciting. And in terms of the integration with the Autoware build system, we use ROS, it's Robot Operating System version 2. And I think it should be pretty simple to integrate it, probably as part of the ROS build system. So a developer can just include it as a ROS package, Don't have to worry about compiling the individual libraries. And then if they have something that uses it, just put it in the package XML, and then you're ready to go. So I think it's going to be something that will be used quite a lot in Autoware going forward. I mean, there will be the kind of initial hurdles that we're going to overcome, but hopefully having strong demonstrators will convince everybody that this is something they should be doing. And then we can show, actually, this was really hard before. Now it's really fast, simple, and it's pretty easy. So you should give it a try as well.
Yeah, it'll be a big snowball effect. People get it working for one thing, and they'll go, oh, but then I just have to do exactly the same thing for this module and this module, and it'll be an accumulative effect, which would be great.
Yeah. So I wanted to take this kind of opportunity at the end to just maybe share a bit more about the Autoware perspective and the kind of work we're doing and how that links in with the kind of UXL initiatives and One API. So specifically on the passenger vehicle side, as I mentioned, unlike the kind of traditional approach with Autoware, which is very research heavy and trying to create a kind of one size fits all Swiss Army knife for autonomous robotics. So you take Autoware and it can run on a robotaxi, run in a warehouse, run in a low speed mobility application. The goal with the passenger vehicle is to actually build more vertically. So to pick one use case and actually take it from software that's at a research phase to a full production commercial phase. And so the kind of thinking and development philosophy is quite different. And it's something that I think lends itself very, very much to this kind of integration early on. So, when it comes to designing the system, it's going to be a vision system, so it'll have stereo vision. So I mentioned the idea of having stereo vision. It's really important because it gives you true depth in the scene. And true depth allows you to know, is there something in front of you or is there something that is not there, irrespective of what it is, whether it's a car, an elephant, a rickshaw, or any strange presentation of a known object. If you look at the crashes that occur with the L2 plus systems, it almost always is the case where the car is driving in autonomous mode and there is a parked vehicle on the side of the road that is a strange type of vehicle. Maybe it is an emergency vehicle, or maybe it is a police car. And the AI system is blind to it because it's a kind of out of distribution class. And radar often is not very good at discriminating static objects. It's very good at moving vehicle detection, but there's too much noise in the static radar point cloud. So most of the time, it's not really considered unless it matches with the vision system. So when the vision system is blind to it, you just have the car go in. And we've seen this happen a lot. And it's one of the open problems in the highway automation system. Can you reliably have a software that can recognize those strange objects, the side of a truck that's turned over, or a fire truck parked on the side? So yeah, I think that's going to be a really interesting thing to develop and to actually be on the journey and have One API kind of be integrated in that kind of the safety part of the stack. And then obviously we will have, the standard neural network approach where you go from image to perception, but there'll also be stuff which is related to end-to-end autonomy. So for example, let's take the case of driving and doing lateral control. So most of the time you will just detect the lanes on a highway and that defines your lateral control. And neural networks, computer vision, you can get that really good performance when the lanes are clean. But what happens when there are no lane markings? Or what happens when there's a snowfall that has covered the lanes, or rain is on the road and the lanes have very bright reflections, so you can't discriminate them. For that part of the stack, we're actually looking to do end-to-end, so going from image to direct prediction of driving corridors. So I think it'll be a really rich stack, and to have a lot of surface area for acceleration using One API. And the requirement to have it run in an efficient way and to run across hardware platforms is paramount for us. Because like I mentioned, we don't want there to be any kind of lock-in for the automotive OEM or for the tier one. They should be able to pick and choose. And I feel like NVIDIA has really captured the space, and there needs to be more open solutions, more alternatives to them. They're clearly one of the forerunners in this space, but I think having Autoware plus UXL together could be like an open source version that challenges the likes of NVIDIA for autonomous driving. And I think that's something that I'm really excited to take them on in this space.
Yep, be great.
Yeah, looking forward to it. Thank you, everybody, and it's been a real pleasure. And please follow the project, follow UXL, follow Autoware, look us up on social media, keep an eye on the GitHub repo because a lot of interesting and exciting things will be happening there. So thank you, everybody, and hope you have a wonderful day.